All right, let's get started. Today we're gonna be solving a medium problem. Let me share the link. Count the number of square-free subsets. You are given a positive integer array nums. A subset of the array is square free if the product of its elements is a square free integer. So we get the definition of square free integer: divisible by no square number other than 1. Return the number of squares free non-empty subsets of the array nums. Since the answer may be too large, return it modulo 10 to the 9 plus 7, the usual modulo. And yeah, here's the definition of a subset in terms of deletion. Okay, and here we get specification. So yes, this means that you can have subsets with the same product, but different combinations of indices with the same values. Okay, and the sizes are up to 1,000 numbers, and this is very suspicious in one sense, or at least it should draw your attention that the values are super small, between 1 and 30 inclusive. So that should be a flag whenever you read a problem and there's such an odd constraint. So we'll see what we can do with that. Hey Lucia, how's it going? And okay, so maybe we can work out some example to make sure that we understand this. Here there are 3. Let's write it down. Why not? 3, 4, 4, 5 is the input in this case. 3, 4, 4, 5, and the answer is 3 if I remember correctly. Yes, but in any case, let's try to figure it out. So if the numbers are already not square free, then we cannot add it to a subset, and that means that 4 and 4 cannot be part of the subsets that we count. And so, well, then it's pretty obvious. We have 2 numbers. They don't have, these are square free, and their product is square free, so we can have all the combinations. We can enumerate them. I mean, there are 2 options for the 3. We can take it or leave it. 2 options for the 5. We can take it or leave it. And so the subsets are going to be, so if we take the 3 and we take the 5, this is one possibility. We can take the 3 and not take the 5. We can skip the 3 and take the 5, and we can skip both. That gives us 4, but they want us to skip this. So that's where the 3 comes from. This is just a detail. I mean, we can subtract 1. The empty subset will always satisfy the condition of square freeness. So it's the same. Maybe it's more convenient to include it, and then we can subtract it at the end, so it doesn't matter. Well, and this is a pretty trivial case. We don't have to work it out. It's obvious that, yeah, we can add, 1 is square free, so we can add it or not, and we don't count the empty set, the empty subset. And that's why we get a 1, only 1. Okay, I think the problem is clear already. So yeah, like I said, we have very, very small numbers, and we're probably going to need a way to check if a number is square free. And one way to check that is to see if there's any prime squared that divides the number. And the number of primes that compose these numbers are just a few, are only the primes less than or equal to 30. So, and those are going to be useful. So let's just hard code them. Why not? I mean, we could write code to calculate it, but given that they are so few, I mean, this is 2, 3, 5, 7, 11. There might be around 10 or something. So let's start by hard coding the relevant primes for this problem, and we could pretty much enumerate them by memory, but there's a trick that I want to show you. We can use Wolfram Alpha, which is a pretty useful tool for LeetCode and in general for programming more numeric stuff, more mathy stuff. We can say something like primes less than 30. We already get some suggestions, some common queries. But in our case, we want this. And I think here's the list. There are 10, exactly 10, so I was right. And yeah, here we have the Wolfram language, which is pretty similar to Python. We copy it, we paste it here. Let's make it a list instead of a set. And that is it. And so now, if we want to check if a number is square free, we can have a helper function that is going to go over all the primes, and we want for all the primes, we don't want p squares to divide our number. And this is very quick because it iterates only 10 numbers in the worst case. So that's one thing. Then what else can we do here? So Another thing that we cannot observe based on the small sizes is that there are going to be a lot of repeated numbers. Because if we have a big array of 1,000 numbers, but they're only in this range, there are going to be a lot of duplicates. So another trick that we can use to compress the input is to represent it as a multiset in some sense. And that could be handy, I think. So let's do that as well. Like we said, well, not only that, represented as a multiset, we can already throw away the non-square free numbers, like we said at the beginning. So let's just transform. This is I like to think about this kinds of pre-processing of the input as somehow changing the representation of the data, which it's an interesting concept because it's very common. So like we said, we want to filter the square free numbers from nums, and then we want to turn this into some kind of multiset, which is a counter. And let's leave it at that for now. So this counter is going to be pretty small if you think about it. Not even less than 30 at the most, because we're filtering the square free numbers. Let me see if Wolfram Alpha knows how many square free numbers between, let's see if it understands, between 1 and 30. So it says that there are only 19. That is interesting. So that means that the len of nums is less than 19. I mean, this is obviously not necessary, but it's interesting. Sometimes it's cool to do some exploration of the data, some empirical calculations for the given constraints. Okay, so let's now get to the core of the problem. Like you can see in the title, we're going to be using dynamic programming. This is a counting problem, and it's pretty common to count using dynamic programming. Sometimes you want to optimize, you want to find an extreme, a minimum, or a maximum using dynamic programming, but sometimes you want to count. Before I forget, let me add the mod thingy here. Otherwise I'll forget. That's a very common bug to have, because here the examples that don't have that case. But yeah, and that reminds me of another thing, that maybe given that this the examples are pretty weak in some sense. I mean, they're not big, there are no, I mean, these two are going to be removed initially, so, and we don't have duplicates then. So the examples are pretty weak, but maybe we can add a number. I mean, an example. Let's add a case because it's pretty easy to add like a big case. We are abusing Wolfram Alpha here. I also found this Chrome extension for doing. Oh, it doesn't show it in the stream, I believe. Okay, so then I'm not gonna use it. Anyways, so let's put this here with square brackets, and let's run it. Let's see if it doesn't break. Yeah, this is because we're not returning anything. We can even print this. Yeah, so this is what I said about this case, but let's go to the big one. And looks reasonable, I guess. And what about this? This should be 19 if Wolfram Alpha didn't lie. Yeah, exactly. Cool. All right. Alrighty then. Okay. So now we have a good test case. Well, I mean, it doesn't have duplicates. Let's remember that in that sense it's not as good as it could be. But let's not worry about that. I guess it's very easy to at least have two occurrences of each number. There we go. Okay, cool. Yeah, sometimes it's a good idea to, for example, in contests, to add a couple of edge cases, big cases, small cases before submitting, because the penalty for getting a wrong answer or a TLE, it's pretty harsh in contests. So I recommend to think about the constraints before submitting and seeing if you can find. Sometimes it's hard to write down edge cases, but sometimes it's not. Sometimes it's trivial, even though, well, in this case it was pretty easy. So I would recommend you to do that. Okay, so this is kind of a very common type of dynamic programming kind of problem, because it's some people call it the take it or leave it structure of dynamic programming. You are counting subsets, so you, for every number that you consider, you can take it, you can add it to the subset, or you can leave it, you can skip it, and that's going to be the structure of our dynamic programming. However, you cannot take it. You cannot always take it. Sometimes you need to know if taking a number is going to generate a non-square free product. Okay, and to do that, you need to remember the product of the numbers that you have added already there. So that means that we need to add a parameter to our DP with the product so far of the product so far. And with that information, we can know if we can take it. If we can take it. Okay. The difference here is that we did this trick of converting this into a multiset, and in that case, the logic is very similar, but instead of taking it or leaving it, you can leave it, or when you can take it, you can take any of the occurrences that you have. So this is a generalization of that pattern, but for multisets. Okay. But the underlying idea is pretty much the same. It's going to require a couple of tweaks here and there. But this is making the algorithm faster because we have this guarantee that the size is only 19, whereas if we didn't do that, the size could be up to 1,000. So it's a pretty big difference. Okay, so it's 2 orders of magnitude difference. So that's why I think it's worth it. I mean, I think you don't need it in this problem, but since it's a good lesson, I'm gonna do it. So one thing that I want to teach is how to write down first the recurrence relation of the DP in a mathematical notation, so that you can think about the recurrence without worrying about the implementation details and the order of execution and so on and so forth. The advantage of writing it down as an equation is that you can ignore a lot of details and you can boil down the core of the algorithm in a very compact form. The drawback maybe is that if you are not familiar with it, you need to learn it, but I think it's worth it. If you have a lot of practice, then you can skip this step. But even if you have practice, sometimes it's good to scribble in a piece of paper the formula, the equation, and only then go to the implementation. So this is going to be something like this. Let's define a function called C. Bear with me because I'm not very tidy with this. So we're going to write the equation for this take it or leave it kind of algorithm. And we said that we needed a second parameter with the product so far. So this C function is going to give us the number of subsets considering the elements from the I inclusive up to the end with the product P, the accumulated product P of the subsets that we already selected, okay? And we will assume that the input is going to be something, we have this counter that we calculated. So let's say that for writing down this, hey Mississippi dog, let me continue with this and then I can answer some questions about Python. I have some pointers that I can give you. But yeah, let's assume that we have the key, which is going to be the number itself, key 0 and the value 0, and then so on up until key k n minus 1 and b n minus 1, and this is going to be our input. So there are going to be a couple of cases. So first, let's think about the base case. The base case is when I is equal to n, which is, we already went through all the elements, and in that case there's only one subset, okay? It's 1, only 1, the count is 1. Okay, then if this is not true, but, and here's there's an edge case because the number 1 is special here, so let's handle it separately. Let's say if k of I is equal to 1, why is it different? Well, because you can add as many ones as you want to the product, and they are not going to change the square freeness of the product. That is not true for any other number. If you add any other number more than once, then you'll have a square, at least a square. So if you have 1, then this was the base case, which does not, this means that it does not depend, it's not recurrent. But in this case, we need to handle the rest of the cases. So this is going to be the count from the other cases, from I plus 1. The product is not going to change because this is, the value here is 1. And we can add any combination of the ones, any combination, since they say that if you have different indices, you have different subsets, then we can have any combination, we can add any combinations, and that is going to give us a different subset. And how many combinations are there? Well, there are 2 to the b of I. Those are all the ways to get the combinations of 1, which also includes the combinations where you don't get any. Okay, so that is another case. And notice that we are not worrying about the mod here. This is just math, so we can ignore it for now. Then, if this is not true, but we have that, let's say that this is, for simplicity, let's say that we have this square free helper, and let's say that P and K of I are not square 3, and in that case, we don't have an option. We cannot add any of the occurrences of K of I. So this is just I plus 1 by times P, okay? And the last case is none of the above, otherwise. And in that case, we can leave it, which is the same as the previous case, or we can add it because we know that it is square free. Well, here is not square free, has only one parameter, okay? So here it's the product, not a comma, okay? And so here again we go to the next number, but in this case we multiply this by K of I. And here's the detail, because we can choose any of the B of I occurrences of K of I. Okay, we cannot choose more than one because of what we said in this case. That only happens when K of I is a 1. Here is not 1. We can only choose one, but we have BI of them. So that's why we need to multiply by B of I. And there you have it. This is basically the recurrence. The code that we're going to write is condensed in this equation. Okay. So I think it's pretty neat that we can write it all down and forget about the details. And the easiest way to map down this into code is to use memoization, a top-down approach. So let's do that. So we said we have the function C. We can use more descriptive names here, like count. Okay. And we had I. We can even just copy it. And this is going to be P. And we have the base case, which is I is equal to N, and we return 1. N in this case is well, there's a detail here that we cannot index a counter by a number, but to be able to have something like we have here, a list of pairs, we can ask for the items and convert them to a list, and now we will have. And maybe to make it correspond to the thing there, we can define the N as well. So this is exactly what we wrote there. Okay. Now we have our second case, which is if, well, let's break this down into K and B, which is what we call them in the formula. And if K is equal 1, then we want to return, let's copy, this is mechanical, count of I plus 1 P times, well, here is where we have to do the mod. So Python has a helper function that does the pow of an integer and with a mod. So we want 2 to the B mod, and then we want to mod the product. So this is our case. And then we are only missing these two cases, which we can write them down. Well, let's write it down similarly to here. Why not? So we have the case where square free, where p times k is square 3, and this was something, and in the I'm reverting the order because it is not a good practice to use nots when you don't have to in a condition, on a conditional. So here we said it was count I plus 1 and p, and here we said it was count I plus 1 p time plus count I plus 1 p times k times b, and we want to mod the product and we want to mod the sum. And this should be it. It's pretty much the same as the formula, like I've been saying. And now we want to call this with the first element, and the product is 1 initially. And this is going to be off by 1 because we are counting the empty set. And yes, it's 1 more in this case. It's 1 more in this case. It's 1 more in this case as well. So let's subtract 1, but be careful because if the count is 0, minus 1 is not in the range. You need to mod. It's not in the expected range. And now we solve them. We have a pretty big case. It ran pretty quickly, 58 milliseconds. I think this is for all 3 cases. So this is cool. Well, before we submit, let's think about the order of complexity, which is a little tricky because here we have this product which is kind of all over the place. I mean, so to calculate the order of complexity, we need to, on the one hand, to count the number of sub-problems. We have that I, it's within 0 and, well, it was 19 inclusive. Okay, so there are 20 possible values for I, but P is a little trickier because it could be big numbers. But one thing to notice is that since P has to be square free, it has to be a combination of the possible primes, and each prime can occur only once. So that means that it's all the subsets of the possible primes. We know that there are 10 primes. So that means that P is 2 to the 10. The possible values of P are 2 to the 10, which is about 1,024. So the number of subproblems is equal to 20 times, well, let's round it down to 10 to the 3. So this is 2 times 10 to the 4. So 20,000. That's pretty small. But here we are Now we want to know the cost of the function, and here we're running square free, which goes over the primes, but that's only 10 in the worst case. So we're going to execute that function this many times, and in the worst case, so this is going to be like 2 times 2 to the 10 to the 5 simple operations. So yeah, this should be very fast. And so now that we are convinced that it should not TLE, and yeah, it's pretty 226. I mean, it's in the top third, which is good. There are other ways to solve this problem. We could use bit masks. I mean, when we counted the possible values of P, we realized that they are all subsets of the primes, of the 10 primes. So we could, instead of having the product, we could have a bit mask, which has an on bit if the corresponding prime is part of the product, and so on. And that might be faster because, well, on the one hand, P could be a little bigger here, a little big. We can, for example, if you do this in C++, you need to be careful what type you use for P, because I don't think it fits in a 32-bit signed integer. And on the other hand, the square freeness of the product could be, if you have bit sets, you could do it with it's an intersection, which is the bitwise AND for bit masks. And here the product would be, if they don't intersect, you could use the bitwise OR operator. And those are usually faster, especially, well, you don't have to do this iteration of all the primes here. You can reduce all the numbers to bit masks, and then this boils down to a problem that doesn't have anything to do with primes. And you start using the bitwise operators and so on. But yeah, before we finish, let's see what so the maximum size that P can have is the whole product of all the numbers. So maybe we can calculate that to see what the bound is. There's a way to do a product, which is this in Python, of a list of numbers. Okay, so here it is. So yes, like I suspected, it's bigger than the max int in C++, because it's like 6 billion, and I think it's a max int is around 2 billion. So yes, in C++ you would have to use long for the type of P, or you could use the other solution with the bit masks, which only requires 10 bits. But yeah, I'm happy with this solution. I think it could run faster if we did it the other way, but I'm pretty happy with this one, so let's leave it at that. So yeah, I think that's all the the takeaways are, I think the biggest lesson, in my opinion, is to abstract the implementation, which means ignoring the non-essential details by writing the recurrence relation as a simple formula, a math formula. Even if we did this with sets for the bitmask version, we would use, instead of multiplication, we would be using intersection or union, but it would be pretty similar. And here, instead of comparing with 1, we would compare with the empty set, things like that. But yeah, I think this is by far the most important lesson that you could use for any dynamic programming problem, solution. And well, then there were, I mean, we followed a path by breaking down. We paid a lot of attention to this flag, which is that the values are very, very small. We use this trick of getting the primes from alpha and just hard coding them. It would be very easy to write code that computes them, but given that it's so small, it's better to just hard code them. We decompose. We knew that we will need this helper function, so we wrote it down at the beginning, and then we figured out this trick of turning, whenever you have a set with a lot of a list with a lot of duplicates, you can represent it as a multi-set, in the case of Python, as a counter, without losing information. And in this case, it was important because it reduced the order of complexity, like we asserted here. And then going back to the formula, the translation of the formula to code was very straightforward, was very mechanical. So that's why I think it's worth it oftentimes. So yes, that's all I have for now. Thanks for watching, and see you in the next one. Bye bye. Hey Kevin. Thanks Lucia. See you guys later. Bye bye.